Okay. Hello, anybody and everybody that's out there. Let me just get myself sorted a tiny bit. Okay, the audio sounds fine. Right. Awesome. Well, hello. So I think it's a pretty interesting thing we're going to talk about today. So if you can't tell from the title, the thing I want to talk about today are white dwarf stars. These are really interesting objects that are one of the end products of stars that have run out of fuel and have stopped being able to burn hydrogen and helium to keep themselves supported against gravity. And they're pretty fascinating in that to really understand them, these things that are, of an astrophysical size, they are, they're stars. So I mean, they're pretty big objects. They're not nearly as big as normal stars because they're actually incredibly dense. But in order to understand these things that are astrophysically speaking, objects of that size, in the sort of star range of sizes, or planet range of sizes more like, we have to actually understand a little bit of quantum mechanics, which is the physics of very, very tiny things. So this is a very interesting kind of mixing of length scales, where in order to understand the behavior of these stars, we actually need to understand a little bit about quantum mechanics, specifically the quantum mechanics of electrons. So what we'll do is first we'll talk a little bit about quantum mechanics and about electrons, and then we'll kind of build up from there and get some important results about electrons, or about more generally particles that have spin a half, of which an electron is one example. And from there, then we'll be able to try and derive this hypothetical upper bound on the mass that these stars can have. So let's sort of give an overview of how these things work. So we looked at stars a little bit previously, or if you watched watched me talk about ordinary stars a couple of weeks ago, you know that stars are this sort of perpetual balance between gravity trying to collapse them inwards and some form of pressure stopping that collapse from occurring, stopping them collapsing down to a point. And in ordinary stars like the Sun, this is achieved by a kind of thermal pressure, because the Sun is very hot. It's got nuclear fusion going on inside it, which generates an enormous amount of heat, and hot things tend to want to expand. So that's how the Sun keeps itself up against gravitational collapse. But white dwarf stars are actually completely different. The dominant mechanism that stops a white dwarf collapsing is entirely quantum mechanical. So it's something we can't really understand in terms of, we know that hot things expand. This is how the Sun stays up from gravity. It's a totally different phenomena that is really interesting and not at all predicted classically. It's something we absolutely need quantum mechanics in order to be able to describe. So that's the first thing we'll do, is we'll try and describe how this quantum mechanics, or this quantum mechanical property that generates this pressure, works. And then by sort of equating this pressure, this maximum pressure that can be provided by this quantum mechanical property, we'll be able to figure out the maximum mass that can be supported against gravitational collapse by this kind of pressure. Okay, if you go beyond this mass, then other things happen and you form an even more exotic kind of star called a neutron star. But in a white dwarf star, the thing that generates the pressure that keeps this thing from collapsing in on itself are the electrons inside of the white dwarf. There's a pressure generated by the electrons due to their quantum mechanical spin, or due to the spin of the particles. So as an outline, what does this pressure come from? Well, there are two kinds of particles, quantum mechanically speaking. There are bosons and there are fermions. And these are distinguished based on the spin they have. And spin, you know, we could spend a long time talking about what spin is, because it's quite a tricky thing to get your head around. And it doesn't really have a good analogy that we can understand in terms of things on our own length scales. It doesn't have a very good classical analogy, but it's a little bit like the angular momentum of the object, but it's an intrinsic angular momentum. You can't get rid of it, and you can't give a particle more of it. It's just a property of the particle. And fermions and bosons are classified based on the amount of spin they have. So we can classify these things. We can say that there are two kinds of particle. There are fermions, which have an odd half-integer spin. So by odd half-integer, I mean something like they have spin a half, spin 3 halves, spin 5 halves, not 5 but 5, 5 halves, and so on. For example, an electron is a fermion, which is the most important thing, which is the particle we'll be paying most attention to today. But we'll also mention bosons. Well, I'll mention them now, and then that's actually about it. That's the only time I'll mention them. But bosons are particles with integer spin, meaning a whole number. So something like spin 0, spin 1, spin 2, and so on. Spin 0 boson is something like the Higgs boson, that is spin 0. A spin 1 boson, like the photon, or a spin 2 boson, like the graviton. Whatever the graviton might look like, all we know really is that it must have spin 0. So there are two kinds of particle, and we classify them based on their spin. Now, in quantum mechanics, I won't sort of start from the beginning of quantum mechanics. Where I'll start is with the kind of fundamental equation for non-relativistic quantum mechanics. And this is called the Schrodinger equation. This equation describes how fundamental particles behave. And the way that it describes how they behave, you'll notice this quantity I'm writing down here, psi, is crucial to understanding quantum mechanics in this way. This function psi I've written down, is called the wave function, and this is closely related to the probability distribution of locating a particular particle, which in this case has some mass m and is moving in some one-dimensional potential I've called Vx. Psi is closely related to the probability of where you might find this particle. Specifically, if you wanted to get the probability from this equation, you would take the wave function and multiply it by its complex conjugate. This is a complex valued function in general, so you have to multiply it by its conjugate to assure that it's real, which a probability density or a probability should certainly always be real. You shouldn't have an imaginary probability. It's not clear what that would mean. So this wave function is the kind of central object in the kind of quantum mechanics we're considering. And you can describe systems with multiple particles using wave functions. It really just means now we're going to add extra variables into the function for a multi-particle system. So this is how I can denote the wave function for an n-particle system. And of course, I'm not going to specify what this will look like, because that'll depend a lot on the particular setup you're looking at. But in general, the point is you can describe the wave function of a particle, the wave function of a system of many particles in this way, where x1 would tell you, would label the position of one particle, x2 labels the position of particle 2, a different particle, this labels where particle 3 might be, and all the way up to the nth particle, and so on. And the distinguishing property of wave functions that describe fermions and wave functions that describe bosons can be seen when you swap the labels on these different particles in this multi-particle system. So if we consider, say, a two-particle system, if we consider fermions, what happens when you switch the labels or switch the positions of the particles for a system of two fermions? So if I switch the position of particle 1 to be where particle 2 is and particle 2 to be where particle 1 was, then you actually pick up a relative minus sign in front of your wave function. Okay. Now, you sort of might think, well, how is that okay if I'm changing what the wave function looks like? Surely what I label my particle as shouldn't affect any experiment or anything I can actually measure. And well, it doesn't, because remember, the way probabilities come out of the wave function is as the wave function times its complex conjugate. So if I include a relative minus sign in here, I'll also include a relative minus sign in here. So these minuses cancel. So just changing the minus sign in front of the wave function doesn't change anything observable, but it actually does have important consequences for fermions. So for fermions, when I switch the positions of two particles in a two-particle system, you pick up a relative minus sign in your new wave function, okay? Whereas for bosons, actually, when you switch the labels or switch the positions of the particles, you actually get exactly the same wave function you had before. There's no flip in the sign. And the proof of this result is actually a very tricky thing to get to. It's called the spin statistics theorem. And it's well beyond what I could, I've never really actually seen a satisfactory proof of it. It's quite a difficult result to prove. But let's sort of qualitatively or kind of very gently think about what this might mean for fermions. If a system of fermions has this property that if you switch two of them around, you end up with minus the wave function you had before. Let's think about the consequences of this. First, we'll be a little bit more precise about how we can get probabilities from the wave function. So if you want to get a probability out of the wave function, the probability of finding particle 1 and particle 2 anywhere in space, so in any sort of range of positions you would want to measure it in, is given by this integral over the two-particle wave function. And this is an integral over x1 and x2. So let me make some room for it. Okay. And in theory, this thing should be 1, because you've got to find the particles somewhere. You know, they can't not be anywhere, so the probability of finding them in any region of space, which is why we've gone from minus infinity to infinity, should always be 1, because they should exist somewhere. Okay. So what about if we set x1 is equal to x2. So we think about measuring both of these particles at the same position in space. Well, remember that if we switch the labels in the fermion wave function, we get this net minus sign once we've switched the particle positions over. But if we have x1 is equal to x2, then what we're really saying here is that the wave function with both particles located at the same position is equal to minus itself. And if something is equal to minus itself, this means that the thing must be identically zero. Okay. So the fermion wave function of having two particles at the same point in space is actually identically zero, which kind of implies to us that you can't put these fermions right on top of each other. They can't be located in the same sort of region of space. They have to be spaced out a little bit more. This is sort of a little hand-wavy way of looking at it. We'll be a lot more precise when we consider the sort of momentum states of these particles rather than the the position representation of them. But what it means is that you can't cram these fermions right on top of each other. They naturally want to be spaced apart because of this anti-symmetrization of the wave function. Okay? So this kind of motivates what is called the Pauli exclusion principle. And the exclusion principle, this is the foundational thing that tells us why white dwarf stars are supported. The exclusion principle is what generates this pressure force that keeps them supported against gravity. And we can summarize this as saying that we can't cram two electrons in a system into the same state. It's not allowed, it's forbidden or quantum mechanically. So you can imagine if you've got these electrons inside of the white dwarf star, if you keep trying to squish the star down and collapse it inwards, what you're essentially doing is you're pushing these electrons closer and closer towards each other. And you might think that, well, even without thinking about quantum mechanics, there should be a repulsion. There should be an electrostatic repulsion, because electrons are negative, and if you try and cram two like charges together, they'll repel each other. But actually, it turns out that the electrostatic repulsion of the electrons is not enough to support against the collapse. The only mechanism that gives you everything you need that will support against the collapse further of the white dwarf is this Pauli force, this force arising from the exclusion principle. Electrostatic forces just aren't enough. So this is the force, or this is the effect, rather, because force is a little shaky to call it that. This is the effect that stops white dwarf stars collapsing in on themselves due to gravity. But there's a fundamental limit to this. There's a limit where it sort of no longer becomes favourable to just have the electrons as they are crammed together into this very close space, and instead it would become energetically favourable actually for the electrons to sort of react with the protons and form neutrons in some way. This kind of inverse beta decay process. And this is how you get neutron stars formed. When the white dwarf becomes too massive, there's this kind of neutron drip that will convert things into convert the electrons and the protons into neutrons and turn into a totally different kind of star. So we want to consider this sort of maximum possible pressure, or this maximum mass that can be supported by the pressure, beyond which, if you get any heavier a white dwarf star, it'll collapse down into some even more exotic kind of star. So there's a fundamental limit to how big a star can be supported by this pressure. And this pressure, this maximum mass that can be supported, is called the Chandrasekhar mass. And what we'll do is we'll first work through some of the quantum mechanics and the kind of statistical physics side of this, and we'll derive, if you have a bunch of electrons in your star, we'll derive an expression for the pressure of these electrons, and then we'll think about what kind of masses can be supported by this pressure generated, which we'll all do from theoretical considerations. But the equations we'll get in the end actually will need some numerical solving. So we won't be able to just rearrange and do things nicely on paper. So we'll write a tiny bit of code that will solve these equations for us and give us a good estimate for this upper bound on the mass, this Chandrasekhar mass. And in the end, we should get a pretty good estimate. The estimate I found earlier was actually pretty accurate, so I was quite happy with it. Okay, so we started off with the Schrodinger equation. Now, to go from here, we're going to think about the time-independent Schrodinger equation in a 1D box. So by a 1D box, I just mean it's confined between two sort of fixed edges, fixed ends. One at x is 0 and one at x is equal to L. YMD. Hello, YMD. Or is that... Oh, Alan MD, you changed your name. Fair enough. Okay. So, what is the time-independent Schrodinger equation? Well, we're also doing it for a free particle, I should say. So that is a particle that is not acted on by any kind of potential. For a free PCLE, meaning particle. Okay. The reason this is a reasonable enough approximation is that it will turn out that the speeds of these electrons is so high that they don't even really see the electric field so much. So they are effectively free particles. They don't really see this electric potential that, of course, is there because of the presence of protons and electrons, but also because we assume these things are kind of evenly distributed, we can assume that there's not really much of an electric field anyway within the neutron star, because there's pretty much a balance of charge, and we'll use that fact later. So the Schrodinger equation looks like this, where E is the energy of the particle, the energy of a particular eigenstate of the wave, or a particular wave function eigenstate. Okay. I should also say, if you want, I have is it possible to have strange quarks inside neutron stars? I really don't know, actually. There are these ideas about lots of even more exotic stars. I think there are ideas that you could have stars made out pretty much entirely out of strange quarks. They're called strange stars as a particular case of a quark star, which are not known to exist at all. I think doing those calculations involving quark stars, so these even more exotic kinds of stars, gets very complicated, because then you're no longer... So here, the quantum mechanics we're doing is fairly straightforward for white dwarfs, because we're just thinking about degenerate electrons. And, degenerate electrons are pretty straightforward to deal with, but when you're dealing with like a quark gluon plasma in a very, in a star, you've got to do QCD, and this is extremely complicated and difficult to do. Numerically and, analytically, these things are very difficult. So I think there's a lot of uncertainty around how these quark stars would work if they exist, and there's no observational evidence for them. But as for whether you can find strange quarks inside neutron stars, I don't know. I'm not sure. I don't know how they would get there. I mean, there are some interactions that don't conserve strangeness, or that violate strangeness conservation. I think the weak interaction doesn't can violate strangeness of quarks. So maybe there are some interactions that could produce strange quarks inside of a neutron star, but I don't know. I'm not sure. We're talking about white dwarfs at the moment. Neutron stars are a whole lot more complicated, because then actually using Newtonian gravity is not even the most accurate thing to do. Then you should really use general relativity to get good estimates on things like the maximum mass of a neutron star, this so-called Tolman-Oppenheimer-Volkoff limit. So neutron stars are a lot more complicated. So I'm going to stick to white dwarfs today, because they're quite nice and you can do most of it by hand. No, not neutron stars today. Maybe we'll do neutron stars another day, but that'll need some GR stuff and, you know, it'll be a lot more complicated. It will be interesting though. But anyway, we can rearrange the Schrodinger equation to look like this. And this is a pretty straightforward ordinary differential equation. This has some general solution for psi. That is some constant times sine of root 2 me over h bar all times x, plus some other constant b times cosine of the same thing inside the bracket. Okay. It's a standard solution to this ODE. Sometimes this is written as kx in terms of the wave number of this particle, where k is now just this root 2 me over h bar. And remember, we're considering this particle confined to a box that has got some size 0 and L. So, has got some length L. It's got one, fixed wall at 0 and one fixed wall at position L. So we have to impose a boundary condition on this. And that is that at x is 0 and at x is L, the wave function has to vanish. Because we're assuming it's, we're sort of assuming it's an infinite potential well. Thank you, Spaceonomy, for following. So the wave function has to vanish at those edges, because the probability of it leaving outside of the edges for a very sort of fixed wall, a very sharp wall, or an infinite potential well, is 0. So it has to vanish there. And if you impose those boundary conditions, you find then that the wave function can only involve sinusoidal terms to it. Okay. So it will be something like sine of, and let's consider now what is the sine thing inside of here. How are you? I'm doing very well, thank you. How are you? So at the moment we're talking about white dwarf stars. Right now we're kind of we're working with some of the quantum mechanics of electrons, and we're going to work up and derive the degeneracy pressure from an electron gas, and then we're going to use this to calculate the maximum hypothetical mass a white dwarf can have, this Chandrasekhar limit. And in order to do it, we'll have to write a little bit of code to solve some of these equations, because they're not analytically solvable. But we'll do that later, and I'll share my screen and show you as I'm writing the code, and hopefully we'll try and reproduce the exact result for it, this number of about 1.44 solar masses for the maximum size of a white dwarf star. I did it earlier. Obviously I prepared it in advance. I did some of these calculations earlier, and I got it pretty accurately to about 2 decimal places. So we'll try and do that, but we're doing it all from scratch, from the quantum mechanics of electrons, all the way up to stellar structure equations, all the way up to finally getting a good estimate for the mass, and doing some numerical calculations to do it. So it's all going to be by hand. Well, I mean, all we're going to be by hand, plus putting it in the computer solve the numerical equations. Okay. So, if you like, the fact that the cosine goes away comes from this boundary condition involving psi 0. Working on a way to state possible differential solutions in Einstein notation. Oh, well, that's cool. Got to learn amazing stuff. Okay, awesome. Cool. So the fact that psi 0 vanishes, this boundary condition, means that we can't have any cosines. Then the fact that psi L vanishes means that we should have A times sine KL is equal to 0. And of course, the trivial solution to that is just to say that A equals 0, but that's like saying the wave function is 0 everywhere, which we're not interested in. So the non-trivial solution to that is to say, therefore, you need sine of KL will be 0. And for sine of KL to be 0, that means KL has got to be some integer number of lots of pi. That is the only thing that makes sine vanish. So we can then write down a general solution for the wave function, which looks like this. Okay, because we found that k must be given by n pi over L. Okay, so that is what our wave function looks like. And we can sketch it, actually. Let's sketch this one-dimensional wave function, what some of these things look like. Here I'm drawing the two walls of the box that prevent the particle from escaping, that confine it to the box. So the wave function, the value of the wave function is going along the y-axis, and then I'm plotting x along here. So n can be any integer value, meaning it can be 0, it can be 1, it can be -1, -5, positive 1,000,000, whatever, as long as it's a whole number value. So we can plot the first two, or the first few, of these solutions. The first not completely boring solution is this one for n equals 1, which is just sort of the first hump of a sine curve. There's a later solution that has two humps. Well, I've drawn it slightly wonky. I want to try and get it so it looks pretty. There's this solution here for when n is equal to 2. And we can draw another one. We can say as well... Come on. Let's draw the n equals 3 solution, which will now have 3 humps to it. Like this. Whoa, not like that. These should all be the same height. The white one, the pink one, and the green one should all be the same height. It's not exactly correct how I've drawn it, but you get the point. They're just sine curves, okay? So these are the first 3 possible states or possible wave functions we can have crammed into this box. So again, remember I said n was an integer. That's why I wrote that up here. So what else did we write down? So what we did here is we said that because of the boundary conditions, you can't have a cosine. So we only have an a sine of KL possible for the wave function. And then we said because also the wave function has got to vanish on the far side of the box at x is equal to L, you must therefore have a sine KL is 0, which means that we actually have these quantized values of k. So k can only take these integer multiples of pi over L. N here has got to be an integer to satisfy this boundary condition. Well, what is k? So, from sort of a bit of lore about what we know about waves and wave-like solutions, k is what you call the wave number. If you were thinking about ordinary oscillations, k would be what you'd call the wave number, which is 1 over the wavelength, okay? And we can relate this to the momentum of a wave, or in different terminology, the momentum of these states here, these wave functions, the momentum these things have is given by h bar, which is the reduced Planck's constant that I'll use throughout. This is just Planck's constant, h divided by 2 pi, h bar times by k. All right? And k, like I said earlier, remember, is this integer number of multiples of pi over L. So the momentum of the particle confined in this way is, wait, let me write it properly, is an integer number of these amounts of momenta here, h bar pi over L. So this first n equals 1 state has got h bar pi over L momentum. The n equals 2 state has got 2h bar pi over L momentum. Okay, so I'm going to give this momentum a little subscript n to show that all of the possible states that this particle can have momentum Pn for the nth state. Okay. Now I said that n could be an integer. Now that means it could also be negative. So I could, if I'd liked, instead of just plotting n equals 1 here, I could have plotted n equals minus 1. But actually this represents the same momentum state, just sort of in a different direction, really. So actually we kind of take this state with n equals 1 and this state with n equals minus 1 to be equivalent. They describe a state with the same momentum. Okay, so I'm only interested in states that have n greater than 0. Okay. So now what I want to do is I want to count the number of possible states in terms of the momentum. So inside of this box, there are actually an infinite number of possible states you can have. Here we've drawn the first state for n equals 1, this white one. We've drawn another state that is labelled by n equals 2 and a third state by n equals 3, but we could keep going. We could go up to 4, 5, 6, 7 and go on forever. So there are an infinite number of possible states we're allowed to have here. Okay. But of course, talking about things in terms of these integers n is not so helpful. What we want to do is we want to talk about these states in terms of the amount of momentum they have in them. And to do that, we're using this relation here that relates the integer n, that kind of labels which state you're looking at, to the momentum of that particular state. Okay. So what we want to know is how many states there are in a certain range of momenta. So we want to calculate how many states are between the two momenta, P and P plus some extra small amount of momenta. Okay. So what we have so far is that P is equal to n times h bar pi over L. Well, now if we're looking to count how many states there are in a certain momentum range, we should think about rearranging this equation for the number of states in terms of the momenta. Okay. So what this equation will tell us is that if you go up to a certain amount of momenta, how many states you're allowed up to that momenta. So say, for example, you wanted to, or say, for example, you put in P is equal to 6h bar pi over L, which is some integer multiple of h by pi over L, so it's an allowed momenta. But if you put that in, what that would mean is that you would find n is equal to 6. So up to this momenta, there are 6 possible states your particle can have. It can be in state n equals 1, n equals 2, n equals 3, or n equals 4. If it has a momenta, well, technically I should say, if it has a momenta that is less than or equal to this amount, then that means there are 6 possible states. Okay. So because of the Pauli exclusion principle that we mentioned earlier, we know that you can't cram 2 electrons into the same state. The exclusion principle says that there's only room for 1 electron in every one of these quantum states, which in this case we're describing in terms of momentum. We're labeling, well, what we've done is we've labeled the different states that are allowed in this box by integers L, but now we've converted these integers L into a labeling using momenta here. Okay, so given that we can only have 1 electron per state crammed into our system, you can only have 1 electron in a certain state in your system. We want to use the momenta to count how many of these states will be allowed in total. Okay. So up to momentum p, there will be this many states allowed, n. So if you want to find out how many states are allowed between p and p plus dp, that will be given by the differential of this. Okay. Okay. But there's something we've slightly missed. So remember, what we were looking for were all of the states with n is greater than 0. We sort of said that these states with n is 1 and n is minus 1, n is 2 compared to n is minus 2 are kind of equivalent to each other. So we actually have to pick up a factor of a half here so that we're only counting these states where n is bigger than 0. Okay. So this expression tells us how many states are allowed between a momenta p and a momenta p plus delta p. Okay. So far what we're doing is we're counting these quantum states because we know that for an electron gas you can only have 1 electron per state. Okay. And if we wanted, we could generalize this to 3D. So at the moment, we've only considered a one-dimensional box. So an electron trapped between a fixed wall at x is 0 and a fixed wall at x is L. But actually, we should think about it being in 3D space. And generalizing this to 3D space is fine. We've now just got, now our wave function solution. I mean, if you wanted to work through the details, you're still solving the time-independent Schrodinger equation that we showed above. Except now, instead of just having a deep psi by dx squared here, you've also got a plus deep psi by dy squared and also a d psi by dz squared. Okay, so it's a 3-dimensional equation now. It's a partial differential equation. But it's a partial differential equation that's very straightforward to solve. It's totally amenable to this method called, what's it called? Separation of variables. So you will write your solution, psi, as a product of the solution, or rather, you'd write it as a product of a function in x times a function of y times a function of z. So when you work it out, what you'll find is instead of having psi equals just this thing here, you would also pick up a m psi y over L, and also multiplied by a sine, now some, or what should I use the symbol for, another integer, capital N, m, and little n, I, z over L. So it'll just be a product of these signs. So this generalizes quite straightforwardly to find how many states you have in this 3D momentum space. And it just becomes 1 over 2L h bar pi cubed. And then you have this momentum volume. So now this px, this py, and this pz are how the width of the momentum range you're considering it for the x-directed momentum, the y-directed momentum, and the z-directed momentum. FS Rooster says, hello fellow physicists. Hello FS Rooster. Okay. So this is now counting how many states are allowed in a certain momentum range, delta px, delta py, and delta pz. Okay. But in fact, we've missed something. What we've missed here is that electrons actually also have an extra thing about them that specifies the quantum state they're in. They have spin, like we mentioned earlier. Specifically, they have spin 1/2. So what we've worked out so far is how many electrons you can cram into a given momentum range, how many states you're allowed to fit in. Remember, it's 1 electron per state because of the Pauli exclusion principle. But actually, because electrons have spin, we're allowed a little more room than we would think. Because electrons have spin 1/2, they can be spin up or spin down. We actually have twice as much room as we would think, because you can instead of just putting 1 electron into one particular state in momentum, you could now have 1 electron with spin up and 1 electron with spin down. Okay, so now we pick up an extra factor of 2 that comes from the fact that electrons have spin 1/2. Okay. You're more of a math person, but you're trying to understand what's going on. Oh, well, I hope you're understanding roughly what's going on. I'm going through it pretty quickly. You know, I mean, the stuff we're talking about today, we're trying to go from quantum mechanics all the way to stellar structure. We're going to do some numerical calculations and some coding. I mean, this is probably combining material from, what, at least 3 different lecture courses you might take a little bit. So it's going to be a little bit rushed, but hopefully it'll get some kind of interest, and then you can always read into things, and I'll talk about some resources and places you can find slightly more detail about these things, because there's so much of great, you know, free courseware and stuff where you can do these things. You're a physics undergrad at OU, very pleased to see more physics on Twitch. Ah, OU, is that Open University or Oxford University? I don't know which, because I think they both kind of claim the OU title. So I don't know which one it is, but either way, that's great. Awesome. Okay, so this is our expression that tells us how many quantum states you can fit into a momentum range dpx, dpy, dpz in a 3D momentum range. Okay, and this factor of 2 comes from the fact that electrons have spin. So because they have spin, there are kind of 2 possible spin states an electron can be in, which means there's we can cram twice as many into a single state. Because now you could have 1 spin up and 1 spin down, and technically they'd be in different states, because 1 is spin up and 1 is spin down, so it's not violating the Pauli exclusion principle. Okay? Alright, so now let's think about, of course what we've got here is we've specified momentum in the x direction, momentum in the y direction, and momentum in the z direction. But in a lot of systems, particularly systems that are isotropic, there's no preferred direction of momentum. Open University, just starting your 2nd year QM course. Oh, right, awesome. Excellent. So in this system, there's no preferred direction of momentum. So there's really no difference between px, py, and pz. So it's convenient to switch to a coordinate system that makes the most of this isotropy. The fact that there's no preferred direction to be thinking about momentum in. Okay? And this is exactly analogous to changing to spherical coordinates in ordinary x, y, and z variables. So I'm changing this momentum volume element into this volume element here, where now you should understand the p here to mean the magnitude of p. just the length of P. This is like, instead of considering volume elements in a 3D grid like this, we're now considering the shells to find the volume of some thickness dp. Whoa, what is that? Some thickness dp and some radius of, say, the inner shell p. Okay. So it's just another way of doing this volume, writing this volume element here. Okay. And we can do this because our system is isotropic. There's no preferred direction of momentum. So px, py, and pz are arbitrary labels. You could just as easily have, you know, swapped the x label with the y label, swapped the y label with the z label, and so on, and it doesn't change anything about the physics of what's going on. In this case, because the system is isotropic in momentum space. So we can therefore write down that the number of states in this momentum interval, where here again, remember, p is the magnitude of the momentum, we've got to carry all of these terms through. So there's a 2 on the top. I've now multiplied by a 4 pi, subbing in for the volume element up here, and I've got a 2 inside of the cubed bracket at the bottom. So if I do all this together, I will get L cubed over pi squared h bar cubed p squared dp. Okay, that is what we get. And now what about L cubed? How should we interpret L cubed? Well, L, remember, we called, for the case where we had one dimension, we called it the length of the box. But then when we added 2 extra dimensions, well, I kept the length the same. I said, you know, the x length is L, the y length is L, the z height is L, but it doesn't matter. I could have called them L1, I could have called them L2, L3, or whatever. But the point is that if you cube this length, this just gives you the volume of the kind of the 3D box we put this thing in. So what I will do is I will rewrite L cubed now as the volume of the system. Okay. And this is an important equation. This equation here is sometimes called the density of states. So it tells us if we're labeling our system in terms of momentum, having a range of momentum between p and p plus delta p, there will be this number of states you can cram in between this momentum range here. Okay, that is how many electron states, and therefore how many electrons, because 1 electron per state from the exclusion principle, how many electrons you can cram into this range of momenta. Okay, when you've got a box that has got some volume v to it. So if you've got a bigger box, a bigger spatial extent, clearly you can cram in more electrons into this kind of this phase space involving momentum and position. Okay, so that is the kind of quantum mechanics bit. That's the quantum mechanics side. We've gone from the Schrodinger equation, thinking about the spin degrees of freedom of electrons. They have spin 1/2, so there are 2 possible states, up and down. And we've derived this expression that gives us how many states are allowed in a certain momentum interval. So now we want to kind of get back a little bit to white dwarfs. So what we're going to do is we're going to assume that the pressure in white dwarfs is due to a degenerate electron gas. We're assuming that the pressure is dominated by a degenerate electron gas. I'm just going to write, well, I'll write degenerate in full. Okay. What do I mean by a degenerate gas? Well, we've described these different states that we're allowed to cram into our box. Remember, we sketched these particles here. So if you have very many particles, what I'm saying is that you can't put more than one particle into this particular state that I've highlighted here. You've got to put one into this state, exactly one into this state, and at most 1 into this state. Now, what a degenerate gas means is that every state is filled kind of from the bottom up. So before we think about filling the n equals 2 state by putting a particle into it, first we fill the n equals 1 state. So the states are filled from the bottom up, counting upwards. So you can say that all of the states are full up to some maximum height. It's like pouring a glass of water. You can't pour, you can't fill the top of the glass before you fill the bottom of the glass. You fill from the bottom up. So up to some particular label that labels which state you're filling up to some particular state, everything will be full, and then above that state, nothing will be full. Okay? This is how we will model, or well, this is the definition of a degenerate Fermi gas. So degenerate means every state is filled up to some upper level. Okay, and as we're labeling these things in terms of momentum, instead of thinking about which n, so I said first you fill n equals 1, then you fill n equals 2, then you fill n equals 3, and so on. Instead of thinking about it in terms of n, we're thinking about it in terms of momentum. And we call this upper level, this maximum state that the particles are filled up to, we call it the Fermi momentum. So in terms of momentum, we call this the Fermi momentum. Or the Fermi level, because sometimes you can write it in terms of energy and so on. Okay? And what we can do is we can calculate this Fermi momentum in terms of the density of electrons inside of the gas. Okay? So let's do that. The way we're going to do it is we're going to use what we've got so far about counting states, figuring out how many states are allowed in a certain momentum range, to calculate the total number of electrons you'd be allowed to cram into a certain volume. Okay? So I'm going to call Ne the total number of electrons you can cram into a particular volume V. Okay? Now remember, we had this density of states. This tells us how many electrons you can put into a volume V within a certain momentum range. So between P and P plus delta P. What we know is that we're filling from the bottom up. So we're filling from P is 0 up to, well, some level above this, some level we haven't yet worked out, but we've called it the Fermi momentum. So what we can say is that if we're now counting the number of electrons in terms of momentum, that the total number of electrons will be the number of states summed up between 0, filling from the bottom, up to some upper level, some Fermi level. Now I'm going to change this because I'm going to fill it in as we go, so I will rub the sum of this out and change it. So we want to count how many states are allowed between 0 up to, the level of the glass that we fill up to. And remember, we've expressed the number of states in terms of momentum using this density of states, as I called it, p squared dp. And we expressed the upper level, the upper state we're filling up to, in terms of this thing I called the Fermi momentum, which we're now calculating. So now our upper bound on the integral becomes this Fermi momentum that we don't yet know. We don't know what this is. It's kind of a weird way of doing it if you've not seen this before. The thing we're trying to calculate appears as the upper limit in an integral. But of course, when we do this integral, we can always rearrange for it, which is what we will do. So this is just a simple integral in p, an integral of p squared with respect to p. And if we do it, we get quite straightforwardly 1/3 v over pi squared h bar cubed and pf cubed. Okay, subbing in this upper bound on the integral. So we've got an expression now that tells us the Fermi momentum. We just have to rearrange for it. So the first thing I want to do is I want to divide by the total volume. Now on the left-hand side, I've got the total number of electrons divided by the total volume these electrons are taking up. And we're going to name this small ne, and we're going to call it the electron number density. That is the number of electrons that you can fit into a meter cubed, or rather the number of electrons you'll find for every meter cubed of volume. Okay, and this is equal to the same expression as above. Now we can invert this expression to find the Fermi momentum, which is what we'll do. So the expression looks like this. And I'm going to keep the NE outside. I could, of course, have kept it all inside of the power of a third here, but I want to keep it outside because we'll play around a little with it later. Okay. So this is our expression for the maximum momentum that is filled up in our gas of fermions, in our collection, in our system of electrons. So every momentum state available, remember, we drew some momentum states. These are all states that here are labelled with an integer n, a particular quantum number, but in fact we can just as well label these in terms of momentum by this identity here that relates n to the momentum. So now every one of these states is filled up to the Fermi momentum that we've calculated in terms of the electron density. So you can see that the more dense the electrons are, the higher this density is, the higher the Fermi momentum will be. Okay. The higher you have to stack them up. So in other words, it's actually harder to stack them when the electron is more dense because you have to end up going to a higher level. You know, you can think of the volume as being, it's like filling up a glass of water where you can shrink the walls of the glass. When you shrink the walls of the glass, you've still got the same number of electrons, you've still got the same amount of water in there. So the water level has to rise when you contract the sort of the cross-sectional area of the glass. So as you contract the area of the glass, as you increase the number density there, you'll raise the momentum that these things have to stack up to, okay, as you decrease the volume. Okay, so we're interested in white dwarfs, so we're interested in the pressure that this gas will generate, because what we've said is that the pressure that supports a white dwarf from collapse is dominated by this quantum mechanical pressure from an electron gas. So we'd like now to actually calculate this pressure. And to do this, we will use a result from kinetic theory, which I won't derive because these things honestly are a pain in the backside, but I'll state it, and then we'll go from there, okay? So the result says that if you've got a single particle that is in an isotropic gas, if it's got some velocity v and some momentum p, then this is the pressure that that particle will contribute to the gas, okay? The third is because it's a factor that comes out when you do the integrals in showing that this thing is isotropic, and the v and the p comes from the sort of equivalent definition of pressure as being the sort of average momentum flux through a surface. The pressure on a surface you can equivalently think of as the rate of momentum transfer through the surface, how much momentum is flowing through the surface. So it's kind of like the third is, you know, we're fluxing the momentum through the surface, and then the factor of a third is a geometric factor because it's spherically symmetric, because we're considering an isotropic gas. Okay? Well, sorry, because we're considering an isotropic gas, not a spherically symmetric gas, because actually that wouldn't be isotropic. Okay, and we know that we've got all of these different particles that are stacked up to some momentum level. But of course, some of them are at this zero momentum level, some of them are higher, 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 and at the very top, there'll be one in this Fermi level, this maximum momentum. So we have to think about how many particles are in each momentum state. Or in other words, how many states, how many electrons can you cram into this momentum range here? Okay. So we need to pick up this density of states factor here. So that is this p squared over pi squared h bar cubed. Okay, so this is like a density of states factor, and this factor comes from pressure of particle in an isotropic gas. Okay, isotropic meaning no sort of preferred direction of momentum, which is like what we assumed earlier when we did this thing where we changed the dpx, dpy, dpz into 4 pi p squared dp. Okay, so this is giving us the pressure of this gas of electrons. Okay, well, in general, special relativity tells us that the momentum of a particle is related to its velocity in this way, as gamma times mv, where gamma is this Lorentz factor, square root of 1 over 1 minus v squared over c squared. Okay, this is this expression for relativistic momentum. Now, we have a v here in our integral, but of course our integration variable, I should also have written down, because we know that our particles only fill up to the Fermi momentum level, our integration range is from 0 up to that maximum momentum level. Okay. Now, because we're integrating with respect to p, we would like to write everything in terms of p, in terms of things we can integrate. Okay. So we want to change this v into a p, and then we can integrate over it. So I have an expression now that relates p on one side to sort of complicated expression for v on the other side, and I can invert this. And I'll spare you the algebra of doing it, but when you do it, you get the velocity is equal to pc over m squared c squared plus p squared, which you can check yourself. You'll just bring this over to this side, square both sides, rearrange for v squared, and then square root to get v. Okay, that gives us v. So then our total integral for the pressure, this big P here is pressure, not momentum. It gets a little confusing because we've got a P for momentum, a P for pressure, and later we'll have a rho for density, which looks a bit like a P, so it will get a little confusing, but I'll try and keep them looking different. So we have an integral from 0 to the Fermi energy. We're integrating with respect to P, the momentum. We have this density of states factor outside of the front, and then the 1/3 Vp, where we've now rewritten V in terms of P, and here is that expression for V in terms of P, will look like this. 1/3 P times V, so Pc over m squared c squared plus p squared. Okay, so that's our integral for the pressure. Now, of course, this is a rather tricky integral to do. Let me just write it out in full with the factors pulled out the front. So it's a c over 3 pi squared h bar cubed. Then we've got an integral of p squared over m squared c squared m squared c squared is just a constant, plus p squared, all square rooted. So this is not a straightforward integral, not one we can easily do analytically. So what we'll do is we'll consider two different limits of it, or we'll think about two different limits of it, and ultimately we'll only really consider one of them, which is more important. So this is the pressure of an electron gas. This integral here, and with the constant in the front, this whole thing will give us the pressure of a degenerate electron gas. But we can do something to simplify this denominator depending on which particular limit we're in. So if the electrons are moving very, very quickly, if they are what we describe as ultra-relativistic. So if the electrons are ultra-relativistic, actually wait, is that the right word? I can't remember if ultra-relativistic means faster than the speed of light. I don't think it does. I'm just going to call them relativistic anyway, because I've forgotten the terminology. If the electrons are relativistic, so if they're moving near the, close to the speed of light, then that means, well, not even if they're moving close to the speed of light. The condition actually is just that their momentum is much, much bigger than m times c, their mass times the speed of light. If this is true, so if we have relativistic electrons in case 1, then you can approximate this denominator here as just being p squared without the m squared c squared, because this term here will dominate. And then you get something very simple. You get the square root of p squared on the bottom, which is just 1 over p. So you end up actually only having... Oh, hang on, we've made a mistake, haven't we? This shouldn't be a p squared. Ah, yep. I missed the p squared in the density of states. My mistake. So remember, there's a p squared here in the density of states. So that carries on down to here. Then we've got another 2 p's here, so this should be a p to the 4th. That's my mistake. So if you get rid of the mc squared here in this relativistic limit, then you just end up dividing the p to the 4th by p, so you end up just taking the integral of p cubed, which is totally easy and something we can do. Okay? So that's very straightforward. There's another limit. So if the electrons are non-relativistic, this means that their energy is dominated by their mass energy, so they're not moving particularly quickly. So their momentum is much, much less than mc. And in that case, if the electrons are non-relativistic, then this term in the denominator will dominate over this term. Meaning now, the denominator, you just have a square root of a constant. So you're just dividing p to the 4th all by mc, which is fine. We just take the mc out the front here, and now we're integrating p to the 4th. So this limit is also fine to do. But we have to sort of ask ourselves which is the important one to do inside of white dwarf stars, particularly as we're considering white dwarf stars that are near the maximum size they can be at this Chandrasekhar limit. Which is the one we should consider, relativistic or non-relativistic? And actually it turns out that the relativistic limit is the correct one to take. This is the most accurate one, because when you've got these things confined at such a high pressure, the electrons will in fact be moving very quickly, and at the Chandrasekhar mass, this is about as high a pressure as you can get within a white dwarf star. So the relativistic limit is the correct one to take, and that's a little bit of a weak justification. There are things you can do to justify much more carefully whether you should take the relativistic or the non-relativistic limit, but I'm not going to do that because we've already spent an hour and a quarter and we've not even got to any numerical stuff yet. So what we're going to do is we're going to assume that the pressure is dominated by this ultra-relativistic electron gas. We're assuming the electrons inside of the white dwarf are relativistic. They're traveling very, very quickly. So their momentum, or rather, so their energy is dominated by their kinetic motion rather than their rest mass. Okay. So we will assume, with sort of some justification I've just given, we will assume that the electrons in a white dwarf are relativistic. Okay. So given we're dealing now with a relativistic electron gas, we can make this approximation to make our integral a little more palatable. So the approximation we're making is now that P is much, much bigger than MC. And with P much, much bigger than MC, that means that we can pretty much just drop it from... Oh, sorry. That means we can pretty much drop the MC part from our denominator, and we end up just with a 1 over square root P squared. Of course, the square and the square root cancel, so we divide P to the 4th by P, and we get an integral P cubed. Okay. And this is something we can calculate. This is something we can do straightforwardly. You know that if you do this integral, you'll raise the power by 1 to the 4th, and then you'll put the quarter at the front. Oh, thank you for the follow, Tiuanda. So if we do that, we get C, and then we get an extra factor of a quarter out the front. So we get a 12 pi squared h bar cubed times the Fermi momentum to the 4th. Okay. So this is our expression for the pressure of a degenerate and relativistic electron gas. The most relevant thing, the most relevant case we have, the gas is degenerate and the gas is relativistic. It turns out this will be the case that is true or is very accurate inside of white dwarfs. Okay. But remember also, we already have an expression for the Fermi momentum. We found earlier the Fermi momentum in terms of the electron number density here. So if we want to, we can replace the Fermi momentum with something that involves the electron number density. Okay. And if we do that, you can again trust me, it's just substituting in the Fermi momentum. We end up with C times 3 pi squared h bar cubed all to the 4/3. This is all over 12 pi squared h bar cubed, and it's all times ne to the power of 4/3. Okay. If you're wondering where I'm getting these numbers from, these are things I've worked out in advance. And if you want to look at them in advance, if you want to look at them as I'm going through them, you can find them if you click on the about section on my Twitch stream. You can go to my website and then click on Twitch office hours, and then at the bottom there'll be a set of notes that talk about white dwarf stars. So this is just all stuff I've written up in advance. It basically goes through everything I'm writing down at the moment, but in slightly more detail, you know, for all of the steps and stuff in between. Okay. So now we've got the pressure in terms of the electron number density, but actually this is not the most convenient thing to have it in terms of. You know, generally when you write down expressions relating pressure of gases, if you want to write down what's called an equation of state, this is an equation that links the pressure of a gas to the density of the gas. Okay. So at the moment we have a number density, not a mass density. But we can rectify that. We can rewrite the number density of electrons in terms of the mass density of the star. So the mass density includes, you know, the protons and other things that are actually inside of the star, the protons and neutrons, okay, that make up the white dwarf star. So in order to convert the mass density into the number of electrons, the electron number density, we can take the mass density, the mass per unit volume, divide it by the mass of a proton. And because the mass of a proton is very very nearly the mass of a neutron, this will give us the total number of protons and neutrons within the star. Now we're neglecting to consider the mass of an electron because it's about 1,000 times smaller than the mass of a proton and the mass of a neutron, so it'll be a very small correction and it won't really matter. So this tells us how many protons and neutrons are inside of the star per unit volume, and now to convert that to the number of electrons per unit volume, we multiply by a factor of a half. And why do we do that? Well, that's because we assume the star is kind of neutral overall, meaning it's got as many protons as it has electrons, which is a good, is a right thing to say. It's a very accurate thing to say. And because of that, for every proton there'll be one electron. So if you're counting the number of electrons, that's the same as counting the number of protons. But what we've got here is the number of protons and neutrons. So again, I suppose here what we're also assuming is that there are a similar number of protons and neutrons, which again is a fairly good approximation because these things all come from fusion of protons in the stars, and then the thing inside the core is almost always balanced between protons and neutrons, the composition of it. Okay. So we can do that. We can rewrite the number density of electrons in terms of the mass density. And now we can just put this up into here. And when we do that, we get our final expression for the electron pressure inside of the star, which is this C over 12 pi squared h bar cubed times now 3 pi squared h bar cubed over 2mp all to the 4/3, and then times the total mass density to the 4/3. Okay. This is an expression that links the pressure inside of the star to the mass density inside of the star. So I'll call this the equation of state of the white dwarf. Okay. An equation of state is something that links pressure to mass density. Now we can write this a little differently. So of course we've got all this, these things out here are all constants, all things we can in theory plug in. So if we do that, well, let me move this all down because it'll take up a bit more space. Oop. I can calculate the numerical value of this prefactor. So I can write this equivalently as some numerical constant called k, that is all of this stuff here, multiplied by rho to the 4/3. And if you actually calculate this numerical constant k, using the value of h bar, the proton mass, etc., you get that it's equal to, I calculated earlier, 4.9 times 10 to the 9. Okay. So this is a number we will plug in later when we're trying to find the Chandrasekhar mass. So this is a different way of writing the equation of state in terms of this actual prefactor, the numerical value of the prefactor. Okay. So what are we doing? So this pressure from the electron gas has to balance the pressure from gravity, the pressure of the star trying to sort of collapse itself inwards by its own mutual gravity. And we derived equations for this sometime before, a couple of weeks ago. So if you haven't seen this before, if you didn't watch that stream, these notes are also on my website under the same heading, the Twitch office hours bit right at the bottom. And these are the notes where we talked about stellar structure. So it doesn't matter if you haven't seen it, but these are quite straightforward to derive. There are two equations of stellar structure we're interested in. The first is the equation of hydrostatic equilibrium. Okay. This is the equation that describes how what a pressure force must be in order to balance the inwards pressure of gravity pulling inwards from the star. So this is the hydrostatic equilibrium equation. And if you want to see a derivation of it, there's a derivation in some notes that are on my website under the same heading I described earlier. Okay. This is one equation, and then there was another equation we also derived, which is this so-called mass continuity equation. So I should say mr here is the mass up to some radius r of the star. So say you've got a star of total radius big R, m little r would be the mass enclosed just up to some small radius, or some smaller than big R radius little r. Okay? So these are the two equations of stellar structure that are going to be important to us. And we actually want to combine these together, because one of these is an equation that talks about mr, although it's the derivative of mr, and there's another mr up here. So the way we go about doing this is if I take the hydrostatic equilibrium equation and I multiply it by rho squared over r, on the left-hand side I now have, multiply it by r squared over rho, I now have this. Okay, just from dividing by rho r, multiplying by r squared. And now I can actually differentiate both sides of this with respect to r. Why do I do that? Well, because I have from the mass continuity equation an expression for delta m over r. So I want to turn this mr into dmr. So differentiating the right-hand side becomes this expression here. And now I have something for this expression from the mass continuity equation. So this dm over r is just 4 pi r squared rho r. So this looks like this. Okay. Now I've got a differential equation only in terms of rho and p. Well, as functions of r as well. Okay. And remember, I also have the equation of state of my gas that says pressure is this constant k that we worked out numerically times rho to the 4/3. So now I can put this expression for p into this expression for p here, and then that'll give me a differential equation only in terms of rho with no dependence on p. Okay. And if I do that, you can trust me that when you plug this in up here, what you end up with is 1 over r squared ddr. I missed an r squared here. Okay, so remember here what I was doing is I was substituting the dm by dr, and dm by dr has 4 pi r squared times rho r. So this should be a 4 pi r squared, as I've now corrected it to. Okay, so that is why there is a 1 over r squared here, because this comes from taking this r over to this side. Okay, so if you put this all together, you can trust me that what you end up with is this expression here. And there's another rho on the right-hand side. Rho. Okay. So this is our differential equation that, if we could solve it, would tell us the density profile of the white dwarf. The point of solving this equation would be to find rho as a function of r. Okay. But this is quite a tricky equation to solve, and in fact it's not one you can solve analytically. You have to solve it numerically. So what we'll do, first of all, is there's a very convenient change of variables you can do to make this equation look a lot nicer. And this is a standard change of variables that takes you to a differential equation called the Lane-Emden equation, which comes up all the time in studying stellar structure and studying the interiors of stars. But we're only going to look at a particular case of it. So what we'll do is we'll introduce new dimensionless variables. By dimensionless, I mean these things have no units. They're a ratio of two things with the same units. And we'll define them as, well, what are they called first? So there is psi, which will sort of be our dimensionless radial distance from the center of the star. And there is phi, which is a function of psi, which will be like our dimensionless pressure. Well, sorry, our dimensionless density, okay, that tells us how the density changes as a function of distance, or in this case, as a function of psi, our dimensionless distance variable. And these are related to our original variables in this way. Psi times k pi g rho to the 2/3 all square rooted. And this is a rather complicated choice of new variable, but it's one that makes things a lot more convenient. And like I say, this is a kind of standard choice. So it's one that there's a sort of recipe for doing. Okay. So this is our variable transformation. This is how we're changing our r and rho variables into psi and theta variables. And now we want to transform this differential equation involving rhos and r's into a differential equation involving psi's and thetas. And this is quite a bit of algebra, so I think I'll spare us from it, but like I've been saying, if you want to see the notes I wrote up beforehand, I do all of the algebra and prove that it's all works out fine in those notes. But what you get to eventually, after you do all the substitutions and transformations you're supposed to do, is you end up with this rather nice looking equation in terms of our new variables. Like this. And this is an example, like I mentioned, of the Lane-Emden equation, which has a lot of study into it because it appears a lot in slightly different forms. So with a different power here, in lots of different models of stellar structure. So not just for white dwarfs, for different kinds of stars too. Okay. So this is our non-dimensionalized, because now our variables psi and theta are non-dimensional. They have no units to them. This is our non-dimensionalized density profile equation. And we can't solve it analytically, so we'll have to do it numerically. Okay. But before we do that, we should think about what we expect the solution to look like. The solution, of course, is that we want theta psi. We want to find a function theta of psi. Why can't I draw psi suddenly? That is satisfied by this equation. Well, remember that psi, as we define the variable, is proportional to the radial distance from the center of the star. So psi is a measure of radius, and theta is this ratio of the core density in the star to the, well, the density of the star to the core density. It's this ratio of densities. I should have made a point of this actually. This rho c, I don't think I defined it, but this is defined as the density of the star at the core of the white dwarf star. So the mass density at the very core. So how do we expect this thing to look? Well, we expect, first of all, that of course the density at the core that we've defined as rho c, well, if you're at r equals 0, that is also meaning you're at xi equals 0. And if you're at r equals 0, you would expect your density rho to be equal to the core density rho c. Therefore, at r equals 0 and xi equals 0, you would expect theta to equal 1, because you would then just have a rho c up here. So we expect that theta at xi equals 0 will equal 1. Okay. We also expect we need two sort of pieces of information to consider, because this is a second order differential equation. It means you need two boundary conditions, or two initial conditions. We expect that the derivative of theta with respect to xi at xi equals 0 should be 0. And this is a little less clear why we expect this, but the reason we expect it is because if it wasn't 0, then we would have a kind of, our equations would have a singularity in them. You would have a point at which the gradient of the density has a singularity. It would flip. Now this will be a little clearer when I draw the sketch. So we expect the density profile of the star described by these non-dimensional variables therefore to start out at 1 here for theta, and we expect as we go further out of the star, further out from the core, that the density should drop, because now there's less material pushing in on us, so you don't need as much pressure and therefore as much density to support against that pressure. There's less gravity squashing in, so the density is less high further out in the star. So we expect it to sort of drop in some way. And what else? We expect when you get to the edge of the star, so when you leave the star's surface, the density should be 0. Because of course once you're outside of the star, you're no longer in the star, there's no material around you, you're in empty space. So we expect at some point that this profile here should cross the x-axis, or the xi-axis here. And this will correspond to the radius of the star r, or specifically this point along the xi-axis I will call xi-r. That is the value of xi that corresponds to a radial distance equal to the radius of the star at this point. Okay. And now the reason we expect this thing to be flat at the top, so expect the derivative to vanish at xi equals 0, is that you have to picture this thing in sort of 3D. So what we've done is we've turned it into a one-dimensional problem by considering only the radius of the star. But if you imagine along every direction in the star, you could take your radial direction at any angle from the center. You know, whatever direction you go out in along the radius, you expect to see the same thing. This is how we've managed to simplify it to a one-dimensional problem. But if you had a particular gradient here that wasn't 0, then it would be kind of like going in one direction, you'd expect it to point up like this, but then if you decided to go in the opposite direction, it would be pointing up again like that, but now there's a discontinuity in the gradient here. It's a little hard to explain, but it's because you don't want your gradient to be singular. at the radius is 0. So you have to have the derivative vanishing there. Okay. So these are actually our boundary conditions, or our initial conditions rather, for the differential equation we're about to solve. And this is just a very rough sketch of what we expect it to look like, and how we should interpret this intersection when it crosses the psi axis. This intersection will tell us the radius of the star. Okay, where this function will go to 0 will help us figure out how big the star is, what its radius is. But of course we can't solve this equation analytically. So we've got to resort to some kind of numerical technique. And I am not a numerical analysis person, but it turns out I tried this with the simplest technique for numerically solving differential equations I know, and it turned out okay, and gave me a value that I was happy with. So what I'm going to do is I'm going to rewrite my equation in terms of variables I can easily copy down into Matlab, because obviously I don't have a theta or a psi button on my keyboard, so I can't type these out. So I'm going to rewrite psi as x, and I'm going to rewrite theta as y. So now my differential equation is just 1 over x squared d dx x squared dy dx is equal to minus x cubed, which is a lot more, minus y cubed, which is a lot more comfortable to see in terms of x and y's when you're thinking about differential equations. So if I expand now this left-hand side, if I do this derivative on this bracket, what I actually end up with is a second derivative of y with respect to x plus 2 over x dy dx, and now I'll bring the minus y cubed over to the left-hand side, plus y cubed is equal to 0. So this is the differential equation I want to solve. Okay. And the approach I take to solving this, oh well actually hang on, I should also translate the boundary conditions. So remember our boundary conditions were that theta at psi is 0 was 1, and the derivative of theta with respect to psi at psi is 0 was 0. So now just swapping the theta for y and the psi for x, this becomes, my boundary conditions are y evaluated at 0 is 1, and dy dx evaluated at 0 is 0. Okay, those are my boundary conditions. Now to solve this equation, the standard thing you do in these numerical techniques is to discretize your axes. Okay, so what we're doing is we're going from a continuous x-axis. Thanks for the free physics course, by the way. Oh, it's my pleasure, no problem. Is we go from a continuous x-axis where, you know, at every single point along here, every single point has got a value assigned to it, a real number value x assigned to it. And we go from this continuous axis now to a discrete grid of points. So now we'll have a point here, etc. And here. So there's no definition at all for what is in between these grids here. Getting the Cosmic C certificate soon. Oh, okay. Yeah, I'm afraid I don't offer certificates. I'll give you an imaginary certificate. We're going from a continuous variable along the x-axis up to now to discrete grid points that I've labeled in blue. Okay. So I'm going to choose to go up to x is 10 here. X is 10 is going to be my the limit I want to solve the equation up to. Now I choose 10 just because in solving this I realized that the crossing point we're looking for this is the thing we're looking for. We're looking for the crossing point because it tells us how big the radius of the star is. I worked out the crossing point, and then I realized, well, I only need to actually go up to about 10 because this thing here will turn out to be less than 10. And as I'm only interested in that, I don't need to go any further than 10 because then it's just pointless information. Because actually having beyond this point, the curve may go on more, as in the equation may be satisfied. The differential equation may have a solution beyond psi r, but that solution has no physical meaning, because now it's telling me that I've got a negative density down here, and of course that has no physically meaningful interpretation. So I'm only interested in going to this crossing point where the curve touches 0. So now my continuous real axis has become grid points, starting at 0 still, and now what I'm going to say is that these grid points are evenly spaced. So they have some spacing that I'm going to call delta x. So the distance to this second grid point here, this that I've drawn in blue, is delta x. The one after that is 2 delta x. The one after that is 3 delta x. The one just before the one at 10 will be delta x to the left of 10, and so on. Okay. And then of course there are grid points in between here. Now the smaller I make this interval between the grid points, the more accurate my solution becomes, because the closer towards a continuous axis my discrete grid points will become. Okay. So now y only has a value on these grid points I've shown in blue. Ooh. So it only has a value on these discrete grid points. Okay. And we can define, or we can label the x position of each of these grid points as being some integer multiple of the spacing between the points. We're saying that the spacing is the same always, so I will call the x position at each grid point xn. We can label it in terms of integers. N is 0, this one will be n is 1, this one is n is 2, and so on. So I will call the nth grid point will be at position n times delta x. Okay, for an integer n. And I will define yn to be the value of the function y that we're trying to solve for, evaluated at the nth grid point xn. Or in other words, evaluated at n times delta x. Okay. So in this scheme, when we've discretized the x-axis, we can rewrite our derivatives in terms of these discrete variables. And what this does is it changes our equation from involving derivatives, it changes it from a differential equation into just a sort of ordinary algebraic sort of equation or a sequence that we can then use a computer to figure out, to find out the next values along that y should take. So the way we do that is we say that the derivative of y with respect to x, evaluated at x, well, you know that when this is continuous, this will be given by something like the limit of x going to 0 of y evaluated at x plus delta x minus y evaluated at x all over little delta x. Well, now that we're no longer dealing with a continuous axis, the closest you can ever get 2 points together is this discrete distance delta x. So now the derivative becomes y evaluated at n plus 1 minus y evaluated at n all over the distance between them that I call delta x. Okay, this is how the first derivative of y is defined, but of course our equation has got a second derivative in it too, so we need to work that out. in terms of this scheme. Doing that, the second derivative, now this is a little different. The way you work this out is you find the ordinary derivative at, say, some point yn plus at yn, as this defines here, and then you find the ordinary derivative at a point yn minus 1. So that will now have yn plus yn here, just yn, not yn plus 1, minus yn minus 1. And then you take the difference between the derivatives and divide that by delta x. You know, the second derivative is just the derivative of the derivatives. And when you do that, you find it's equal to this. Okay. This is how the continuous second derivative becomes when you put it on a discrete interval with this fixed step delta x. Okay, that is what these things look like. So now what we'd like to do is we'd like to rewrite our differential equation in terms of these discretized variables. Okay, so we want to replace everywhere where there's a y with yn. We want to replace x with xn, and we're going to replace these derivatives by the expressions we've just found. Okay, so doing that, this becomes yn plus 1 minus 2yn plus yn minus 1 all over delta x squared. That's for the second derivative here. Plus 2 over, now the x will become xn, and xn, remember, is just n times delta x. The dy by dx we found before was yn plus 1 minus yn over delta x, and the y cubed, well, the y now becomes a yn. So plus yn cubed is equal to 0. Okay. That's how our equation changes when we put it on a discrete grid. And what can we do now? So now what we'd like to do is we'd like to rearrange for yn plus 1 in terms of yn and yn minus 1. Because then, if we know yn and we know yn minus 1, we can always find yn plus 1. So it's like, if you think about these grid points, we can always use the 0 grid point and the 1 grid point, and those two will tell us the third grid point. Then after that, we can use the first grid point and the 2 grid point to tell us the 3 grid point. Then we'll use the 2 grid point and the 3 grid point to tell us the 4 grid point, and so on. And we evolve it forwards until we know all of these grid points. Okay, and if we use very tiny steps, so a very small distance delta x, this becomes increasingly accurate to what the real function looks like defined on this continuous line. So it's a way of getting sort of a cheap numerical solution, which is not conceptually hard to follow, I don't think. Okay. So if we rearrange all of this for yn plus 1, what you find if you do this is you end up with yn plus 1 is equal to 2 plus 2 over n yn minus y over n cubed minus yn n minus y minus y n minus 1, sorry, all over 1 plus 2 over n. Okay, so now you can see if you know two values n minus 1 and n, you can then use these to work out the n plus 1th value. Okay, so this is no longer a differential equation, it's an algebraic equation. And we've just got to think about whether or not we know, for example, y0 and y1. Because we need to know these things to then work out y2, and then we need to use y2 and y1 to work out y3. So y1 is y evaluated when n is y0 is y evaluated when n is equal to 0. So n equals to 0 is just evaluating y at the 0 grid point. So this is just y0 that we have from our boundary conditions here. So it's the same thing. The y0 there is just also equal to 1. Now y1, the boundary condition we have already is that we have dy by dx evaluated at 0 is equal to 0. Okay. Now if we write this in terms of our discrete variables on this grid point, these grid points we've defined, this will now become y1 minus y0 over delta x is equal to 0. Okay. And this expression tells us that therefore y1 must be equal to y0. So actually y1 is also 1. So this is our important numerical equation. It tells us how to evolve our system forwards, starting from y at x is 0 onwards to all of these other values of y as far on as we'd like. Okay. So we can do this. We can now program this, what it should look like. Okay. And let's do that. Wait a minute. Let's do that now. Okay. So if I click that. Okay. You now should be able to see my screen. So you can now see Matlab, I expect, on my screen. Okay. So I'm going to do this in Matlab. Because it's, you could do it in any language you want, because there's nothing specialized about this. It's all very... Oh, where did I get the white dwarf animation? Oh, that's from Space Engine, not Universe Sandbox. So yeah, I haven't actually pointed out anything to do with this yet. But this is a nice animation of Sirius A and Sirius B. So this is a binary star system. Sirius B is the white dwarf you can see here, and Sirius A is, I think is Sirius A a red giant, or it's some ordinary star, not a dead star anyway. Here, and they're in a binary star system, and it doesn't actually look very interesting up close, to be honest, in this animation. But I mean, to be honest, I don't think white dwarf stars are particularly interesting up close. The most interesting things about them happen when they get very close to the star that they're around in a binary star system, and then they can start to kind of pull material off of it, and do some real damage and do some interesting things there. But in terms of just being on their own, just sitting around, they don't do a great deal. Sirius B was once interesting. Yeah, well, I mean, it's still interesting when you think about what's going on inside of it, but I mean, I don't actually know whether Sirius B pulls material off of Sirius A. I don't know how close they are. That is the dog star, that's right. Sirius is the dog star. You can see it up in the sky, Sirius A. You can't see Sirius B, of course, because, white dwarf stars are much less luminous than ordinary stars, and also much, much smaller. So there's no way you could possibly resolve, seeing Sirius B going around Sirius A. But you can infer its presence based on the kind of wobble that Sirius A shows. So if you take very detailed measurements of Sirius A, you can see that as these things orbit around each other, Sirius A will kind of wobble to the side. Although you can't see the white dwarf that is doing it, you can infer that there must be something very massive, but not very large and not very luminous, such as a white dwarf, that is causing it to sort of wobble a little bit. So this is how we know it's there. We know it's there from its gravitational effect on its sister star that it's orbiting. Okay. But yeah, exactly, it's known as the dog star. So let's take a look. What was I doing? Right, yeah, I'm showing you my screen now. So now you should be able to see my command window here on Matlab. So now we're going to try and implement, will you see a Doppler shift? I don't know if the wobble is that significant. I don't think it's quick enough to do that. I don't know. I know that they can. Can't they do some like Doppler shifty measurements to like detect exoplanets based on how they move? So like when an exoplanet is moving around a star, when it's moving towards you, it's it will slightly blue shift. When it's moving away, it will slightly red shift. I think you could use those measurements to calculate the orbital speed, but I don't know whether Sirius A wobbles enough that you can calculate, or you could measure any kind of redshift or blue shift from it. I don't know. I'm not sure, actually. I'm not sure how much it would wobble, whether or not it would be enough to measure that. I'm not totally sure. Okay. But now what we're trying to do is we're trying to implement this numerical equation we've just figured out. So I realize actually you can't see the numerical equation on the screen. Maybe I can change that if I just how can I do that? How about if I drag this? Then okay, then you can kind of see that, can't you? I think. So now you should be able to see the equation we're trying to get to and what we're going to program into Matlab in order to do it. Okay. All right. So this method, I should say, that we've done to program it is called the explicit Euler method. This way that we've discretized our coordinate grid. Okay. Oh, why is it showing the directory? Stop it. Okay. So first we're just going to clear all our variables in case there are any things that I've cross-defined that I want to then define later under the same name. And now what I'm going to do is I'm going to call... I hope my keyboard isn't too loud, by the way. I realize it's right next to my mic. I didn't actually think about how loud it would be, but I assume it's tolerable. Oh, I didn't finish my tea. Well, that is really cold. There's a cold tea. You like the presses. Why would you like them? Anyway, so I'm using H to denote the time steps now instead of delta x, because again, there's no delta key on my keyboard. So I'm going to use time steps, or steps between my grid points, of 0.02. Okay. And if I'm going between x is 0 and x is 10, you're referring to gravity redshifting, right? No, not gravitational redshift. This is redshift due to these things orbiting each other. So if you imagine, you're looking along the line of sight and you see a star, as a planet's going around the star, when it's at this stage in the orbit here, it's moving towards you. When it's at this stage, it's moving away. So at this stage, the light is redshifted away. At this stage, the light is blue shifted, higher frequency towards you. So not gravitational redshift. That would be far too weak to measure from a star or something like that. Okay, definitely from a planet anyway. Certainly too weak to measure from that without extreme precision. Okay, so I'm setting the distance between my grid points as 0.02, and remember I'm going from x is 0 up to x is 10 because I'm looking for this crossing point here that you should be able to see. Wait, maybe you can't see it. I can't remember where. I can't remember where I put the board. Okay, wait. The crossing point there. So I'm going up to around x is 10. That is like here or something. Okay. So that is where I'm going to. Let me put the thing back on. Ooh. Okay, there. So I'm going from x is 0 up to x is 10. And if I convert that into how many grid points I need. So the number of grid points I need will be roughly the distance I'm trying to go over from 0 up to 10 divided by the distance between each grid point. Okay, so that means my total number of grid points is going to be the distance I'm going to between 0 and 10 divided by the number of grid points. But of course, depending on which h I put in, it's not actually guaranteed this thing will be an integer. So I put in a ceiling function which just rounds up. So now this turns this total number of grid points into an integer. Okay. What next? So now the point is I'm going to specify y1 and y0. Remember, these are things now we know, y1 and y0. I will specify these, and then I will use the values y1 and y0 to find y3 and then y4 and so on. So what I do is just standard practice, is I make some room for these variables. So I define as a 1 by n matrix that is totally empty. It's just got zeros in it. The reason I do that is then so later on I can define the nth element in this matrix in some way. Now what I need to specify is that the first value of y1, this boundary that we gave, remember, which is here. Well, here I've called it 0, but I mean, it doesn't really matter. All it means is it's the first one. The fact it's a 0 and not a 1 is unimportant, okay? So I'm going to call that, well, that rather has the value 1. I also found that y2, or as I've written it here, y1, but again, it doesn't matter, is also 1. Okay, and now I need to write a little bit of code that will go through for every one of these n values. So we'll calculate from knowing 0 and 1, we'll calculate y3, and then after that we'll use 2 and 3 to find y4, we'll use 4 and 5 to find y6, and so on and so forth, that will do all of this. So to do that, I'm just going to use a simple for loop, okay? So I'm going to say for small n is equal to 3 all the way up to big N, which is my final limit. I'm going to define yn as, and now I just have to input this expression I've got here, okay, which is a little bit of a hassle to put in, but it doesn't matter. So it's 2 over 2n all times yn. This is in the numerator. I'll do the numerator first, and then I'll put it all over the denominator. And that is minus yn all cubed and minus yn minus 1. Okay. Now I put that entire numerator in a bracket, and then I have to divide by the denominator, which, as you can see, is 1 plus 2 over n. Okay. So that all looks fine. 2 plus 2 over n times yn minus yn cubed minus yn minus 1 all over 1 plus 2n. That looks fine. And I'm not going to comma it because I want to see it tick through these values, because then it'll tell me, you know, how long it's got to go and so on. And it'll show us it's not just frozen, which is always nice. And then after we've done that, I want to plot x against y. So I want to plot the graph, how this thing looks. So the x values, remember, are these integer multiples of delta x, or y as I've called it here. So my x grid points will be given by h, my grid spacing, multiplied by 1 up to n, all of these grid points, and against that I'm going to just plot y. Okay? Right, so let's see if it runs. Okay, it is doing something. Now it'll probably take a couple of seconds for it to work through, because we've used a fairly small spacing to do it, but once it pops up, it should give us a fairly nice looking plot, and then on that plot we'll be able to eyeball where this crossing is that corresponds to the radius of the star. Okay. So we'll just give it a little bit longer. I don't think there's anything wrong with it. It seems we've done everything as I did it earlier. It'll just take a little while. Yeah, while we wait. What do we do while we wait? I mean, I'm just going to finish my very cold tea. When are we having piano streams? Why would I play the piano? I mean, I do play the piano, but how do you know I play the piano? Well, I guess you can see my piano sometimes in some of my videos. There's a wonderful series of lectures by Carl Bender on numerical analysis. I find the subject fascinating. Yeah, I should really, you know, it doesn't come into much of my work, to be honest. So I don't know a great deal about it, but I mean, what I'm doing here, you know, is pretty inefficient, as you can tell. Oh, whoa, something's gone wrong there. That's not right. Yeah. Okay, we have made an error. Something has gone wrong, because that is not what it should look like. What have I done wrong? Okay, let me see. So we defined the step length, that's fine. We've got n, the thing we're going up to. I've defined my y, I defined my initial y1 and y2 points. There must be an error in something we've done here. What have we done? So I'm now comparing it with the expression 2 plus 2 over n, all times yn. That's fine. Minus yn cubed, that's fine. Minus yn minus 1, that's fine. And that whole thing is in the numerator over... Ah! Aha, I know what we've done. Okay, so I've said yn is equal to this. Okay, no. So this here should be a n minus... This should be like... Yeah. This should be an n minus 1. This should be an n minus 1. This should be an n minus 2. Okay. So this is... Okay, wait, no. No, let me do it differently. So now I'm going to say I'm going from 2, and this is n plus 1. Okay. That's what we did wrong. I accidentally put a yn on the left-hand side when it should have been a yn plus 1. Okay. Amazing he gets the accuracy he gets for just 7 numbers. Yeah, that sounds interesting. I've not heard of this series, but I'll take a look for it. Okay, so now this should work. Right. Now we just have to wait again. Now this should be quicker because now this is actually going to... I thought it was taking a bit long before because clearly it was doing some weird asymptotic stuff at x is 0. But now it's going to actually, hopefully the right one, it should give us something... Oh, I've just realised something actually though. We're going to have a problem when it gets to... Okay, wait. No, I'm going to change this. I'm going to keep that as a 3. Keep that as an n. Then this will be an n minus 1. This will be an n minus 1. This will be an n minus 2. Okay. Okay, I'm happy with that now. That'll be fine. Hopefully. That's exactly what I coded earlier. And that worked out fine. So hopefully that'll be okay. We'll see what happens. I need some like elevator music while it's running through the numbers. I thought it's better to put it so the numbers come up, because then you can actually see it kind of working as it goes through. Yeah, it's just gonna keep ticking on for a bit. Oh wait. Oh no, I didn't. I missed something else. Ah, I've just realized this expression here is actually slightly incorrect. There should be a delta x squared here. I'm gonna have to change that. There should be a delta x squared here. If you think about rearranging this for yn plus 1, if you multiply the whole thing by delta x... Oh wait, you can't see this, can you? If you think about rearranging this thing here for yn plus 1, you end up multiplying the whole thing by delta x squared. So you should have a delta x squared here, but I haven't got one. So now I have to put in a delta x squared here, which is why, again, this has given us something totally crazy. Okay. Okay, now this time it'll definitely work. Now I know what's wrong with it. So now there's a h squared in here. Okay. Alright, this time it will definitely work. I'm certain. Okay, we'll see. Yeah, that was a dumb mistake on my part. I'll have to correct that on the notes I put on my website. Okay, let's see. I think it's gonna work. If it doesn't work, I mean, I don't know, what forfeit can I... I'm not gonna think of a forfeit. What can I do? I don't know. What's a forfeit I'll do if it doesn't work? Someone can suggest one. I mean, if it's ridiculous, I obviously just won't do it. But you can try. Music again. Oh, what is the theme I was humming before? It was like, is it Jeopardy or something? No, it's not Jeopardy. Well, it's like bum 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 ba bum 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 ba 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 bum 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 ba bum. Oh no, I'm not going to play the piano. I don't know how I'd hook it up to the stream anyway. Oh, come on. I bet it's not going to work, actually. I bet there'll be some stupid thing I've not considered that I've got wrong that will mean it doesn't work. I mean, it should work. There's no reason it shouldn't work. What I've written down appears to be identical to what I did earlier when it did work. But computers are silly, so it may look identical, but it may end up totally different. I mean, it's certainly taking a while. I should have tried... You know what I should have done? Is I should have tried it with a larger time step, a bigger value of x beforehand, and then it would have been a lot quicker, because we'd have a lot fewer grid points. Ah! No, it works. Brilliant. Woo. Sweet. So yeah, this is kind of like the shape we were expecting before. Now, it's a little hard to see because it's just a little thing at the bottom here, but remember the shape we expected before was this kind of thing where it starts off at 1, will come down somewhat, and then it'll cross the axis at some point. So you can see if you trace along from 0, this does indeed cross the axis somewhere, and it appears to cross, you know, around sort of 7-ish. We don't know exactly where, but it's around 7. But we should calculate where it crosses a lot more carefully, so let's do that. So we're looking now for this psi r. This is what we're searching for because it will help tell us the radius of the star. Okay? So now let's write a little something to tell us where this crossing is. Sigmoidal. Yeah. It's not some crazy oscillating thing. That's good. So now we want to find this crossing on the axis that I'm going to call xr. Okay? Well, we want to find the 0 of the function. By the 0, I mean the thing where this thing crosses would cross the x-axis. Okay? The wavy one was cool, yeah. But, you know, it's cool, but it wasn't physically meaningful. So maybe it's not so cool anyway. So the way I'm going to do this is think about what we've got. We've got this grid of 5,000 y points that correspond to all of these values along here. And we want to search for the one that crosses through 0, or the one that comes closest to crossing through 0. So the way I'm going to do that is I'm going to interpolate. I'm going to find all the values of y that are bigger than 0, find all the values of y that are less than 0, and then I know that the one that, you know, the one that lies in between there has got to be the one that crosses 0, or the one that's closest to crossing through 0. Okay? So I'm going to look for f min, I'm going to call it, which is like the element of the matrix of my y values which is the smallest element that is bigger than 0. If you think about this thing, remember, it's going from bigger than 0 to then smaller than 0, okay? So F min will be like this point here, somewhere. And of course, because as we've seen, this thing then goes on further negative, as we saw in our real plot. F max, as I'll define shortly, will be like this point here. So I'll interpolate, and then in the middle I'll find psi r, okay? So that's what I'm going to do. So F min, what I can do to find that is I will search for y is greater than 0, okay? And then this value x min, the point that corresponds to that matrix element, will be it will be h times, and then it will be the final value of f min. So f min, drop my pen. So f min will give us all of these matrix, all of these elements of my vector that are greater than y. So to the left of this point here, f min will tell me all of these, you know, n equals 1, n equals 2, n equals blah, 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 all the way up to the final one that it's such that they're greater than 0. And the one I want that is closest here to where the crossing is the one at the very end. So I'm looking for, that's why I'm evaluating f min at the length of x min, the length of f min at its final value. Okay, so that's how I define f min. Then f max I define similarly, where now I'm looking for the values of y that are below 0. So that corresponds to, you know, the curve carries on like this, all of these values here. And now I want to find the one that is furthest to the left, so the first of these values to the right of xr, okay? So now I define x max, as I call it, as f max, well, as h times f max evaluated at 1, okay? And I'm going to comment these things because they'll give me some, they'll spit out a lot of numbers when I do it. And then I'm going to define xr, which, remember, is, because I'm now denoting psi that appeared in our equations as x, this you can think of as psi r, will be the mean of these two things. So it's the mean of x min. Ooh. Where's the square bracket gone? Ah. X min and x max. Okay. So let's see what that gives us. That gives us xr is 6.887, which it turns out is very accurate. So this is very good. So we can now, let me switch back to just the screen. Okay. So we figured out from this numerical calculation that psi r, or xr as it was called when we were doing the coding, is equal to 6.8870. Okay. Wait, is this even on the... Yeah, this is below. Okay. So this is what we wanted. And now remember, we did this variable transformation from initially, think all the way back, we had our our density differential equation for the density function. Density is a function of r within the white dwarf, and we transformed it using this variable transformation to give us a differential equation involving psi and theta. But remember, r and psi were linked in this way. So if we found that psi of r is this value 6.887, and r and psi are linked in this way, then that means that r is equal to psi of r, or psi r, times this thing in here. Sorry, this should be a rho c here for the core density. Okay. And remember, we've calculated this constant k before. This was all this stuff involving the mass of a proton and c and all of this other Planck's constant and things. So we calculated earlier that k was 4.9 times 10 to the 9. And if we put the value of k into here, we put the value of psi r we've calculated numerically into here. If we put all these numbers in together, what we find is that the radius of the star is about 3.33 times 10 to the 10 times whatever the core density is to the minus a third. So this is how the core density appears here, okay? So that'll be an important equation. This tells us how the radius of a white dwarf star will depend on its core density, okay? But remember, what we're searching for in trying to get to this Chandrasekhar limit is the mass, right? We're trying to get to the mass of the star rather than the radius. So how do we do that? Well, we now have a sort of numerical expression for the density. You know, we don't have an equation for the density. What we have is the plot. Remember the plot I showed up earlier that we calculated. This is theta as a function of psi, but remember theta is related to density rho and psi is related to radius r. So we actually have the density profile, r theta as a function of r. And if you want to calculate the total mass from that, that is just the integral from 0 up to r, the total radius, of the density rho r, the density at a certain radius, times 4 pi r squared dr. Okay, this will give us the total mass of the star. And now we've calculated this in terms of the core density. We have numerically solved for this. We have it saved in my computer. We've got this these y values that correspond to theta values, and remember theta is just a variable transformation away from rho. So what we can do is we can rewrite this in terms of psi instead of r, and theta instead of rho. Okay? And remember how these things are defined. Remember r is defined as psi times k over pi g rho c to the 2/3, all square rooted, and rho is related to theta as rho is the core density times theta psi all to the power of 3. Well, with theta to the power of 3. Okay? All right. So now what we want to do is we want to rewrite our integral for the mass of the white dwarf in terms of our dimensionless variables. And the reason we want to do this is because we've already got these ready in the computer. You know, these are the things we've been calculating with so far. And again, this is a rather lot of algebra. You know, everywhere you see an r, replace it with this expression. Everywhere where you see a rho, replace it with this expression. Wherever you see a dr, convert dr into a d psi times this thing. Change your limit for r into psi r, and you know, it goes on a little bit. But the point is you end up with a totally sensible expression for the mass. When you do all these variables, carry through all these constants, are extra careful, and you know, pray to whichever one of your physics gods you'd like to pray to, you get an expression that looks like this. So we have a constant out the front, and then we have this dimensionless mass integral. Okay. So these are all things we can evaluate. Remember, K we calculated earlier in terms of the proton mass, Planck's constant, and so on. We found it to be about 4.9 times 10 to the 9. G, of course, is a constant we know. Pi is a constant we know. Now, what you'll notice, interestingly, is that the core density has actually dropped out of this expression. Now, this isn't a mistake. This isn't something we've done wrong. Remember, the density is proportional to the core density. So from here, here we'll get something proportional to core density, and then from all of these prefactors, you get a cancellation in all of these powers of 2/3 and these square roots and all these things popping up, and the core density actually cancels. So the mass of the white dwarf actually is independent of the core density. Okay, at this kind of maximal mass anyway, when the pressure is on the boundary of if you increase the mass any more, as it is how we're considering it now, the star would collapse. At this point, the mass becomes independent of the core density. So there's no expression involving the core density here, which is good because now we don't need to make a guess for the core density because we don't actually know what that is. So now we can go straight ahead and calculate the rest of these things. So if you plug in the 4.9 times 10 to the 9 we calculated earlier for K, put in pi, put in G is 6.67 times 10 to the minus 11, then you 3 over 2 root it, and times by 4 pi. This whole thing becomes, to 2 decimal places, 1.42 times 10 to the 30 times by this integral. Okay. And now this integral we can do numerically, very straightforwardly. So we have saved in the computer, we've got these values for theta psi. We know what theta r is. Remember, theta r was 6.887. So now we know we just have to integrate these values here that we know up to 6.887. Which is straightforward to do. This is just really a trapezium rule thing. So let me switch back to Matlab. Okay, and now you should be able to see it. Now we can just program this in again. So now I want to find this integral I wrote down. Let me move my screen again. I'll just put it there for now. Actually, no. Let me leave it there, and let me just move it around a bit. Oh, that's good enough. That's good enough. You can see it there. Okay. So now I want to compute this integral numerically. Okay. Ooh. All right. Excellent. So now I'm trying to find this dimensionless mass integral. So I'm going to define my x-axis. So remember, at the moment I've defined x as being integer multiples from 1 up to big N of this grid spacing on this discretized x-axis of a grid spacing h. So I'm going to define h in this way. 1 up to capital N. This now defines my x-axis as being these discretized grid points. And then the thing I'm going to use to calculate this integral, which I'm going to call b, this whole thing here, I'm just going to call it b. I'm going to use an inbuilt Matlab function because I'm being lazy, and I'm going to use this cumtraps function. which is a bit of a funny name. And really, all you have to do is you have to put in the x variable you're integrating through. Yep, we are using Matlab indeed, Atom Fighter. And we're being a bit lazy because we're not even doing the programming a trapezium rule ourselves. We're just using an inbuilt function. But I guess, you know, I mean, all physicists are lazy, really. If there's an inbuilt function that does it, why would you program it? Yeah, exactly. Cumulative trapezoid. Oh, thank you for the follow, Atom Fighter. Very nice of you. Okay. So we're doing the cumulative sum of these trapezoids. Exactly. Why have Matlab if you won't use it? And we're integrating. Now again, remember we're switching. When I write y, I mean theta. When I write x, I mean psi. So I am. I like how my auto mod didn't want my auto moderator tried to block the phrase "cum traps." Probably for obvious reasons, but it clearly doesn't realize it's a perfectly sensible MATLAB MATLAB command to be using. I think it's got a dirty mind. That's not your fault. Okay. Yeah. The auto mod's ahead of us. It knew what we were thinking. So we're integrating over x. So we put an x here just as part of this definition of the function. And what we're trying to integrate is x squared times y cubed. Remember, theta is y, psi is x. Okay. So I put in an x squared and a y cubed. It is the correct command, yes. Okay. And when I do this, well, let's do it first. Let's show what this function gives us. What it gives us is the integral up to each one of these x values that I've inputted. So if I plot b, where's it gone? You can see that it gives us a cumulative distribution. Okay. Is there a cumulative sum? Yeah, I expect there is a cumulative sum function. Okay, we can start talking about cumulative functions now. It's making me giggle. Okay, so you can see that at some point this cumulative distribution here will start to go down, and we understand that as being when our function becomes negative. So what we're looking for is we're looking for the particular value of this cumulative sum of trapezia area up to its peak. So up to the point where the function we sketched earlier, which has gone now, crosses the x-axis. That's what we're looking for. Okay. So in order to select that, I am just going to need to select the value of the cumulative sum function up to the f min I defined earlier. Because remember, f min, let me go back to where I was earlier. F min, if you remember, is like the grid point closest. Oh, the grid point closest to the crossing. Okay, so the closest I can get grid point wise is here, and then if I take the cumulative sum up to here, that'll give me the integral of, well, it won't give me the integral of this function exactly, but the integral up to where I want to go up to, which is this outer radius r. Okay. Now I know you can't see all of it. It's just you can see the part of it I mean, which is here. Don't worry. It's yeah. I haven't thought about exactly how to display this most optimally, but I just wanted to show this point here. Okay. All right, it's fine. Don't worry. This was just an aside point to make something clear. What am I doing? Right, and yeah. Okay. So I want to evaluate b at the length of f min. So at this point where we're just to the right, just to the left of the 0. And if I do that now I'm going to suppress this output here because I don't want to see all this nonsense. I will get 2.016. which is good. So now if I come off of this and send Matlab away and check my audio's not died. Okay, it's not died. Sometimes my audio does weird things when I remove a window, but it didn't do it luckily. Okay, so what we found numerically, we've just found that the value of this integral is 2.0136. Okay, so that means this total mass we've figured out of the star is the 1.42 times 10 to the 30 from before, now times this 2.0136, or in kilograms, 2.859 times 10 to the 30. Yeah, Matthew de Pryor is jumping ahead. This is certainly of the order of magnitude of the mass of the sun. This something times 10 to the 30 kilograms. And if we write this in units of solar masses, we get 1.44 solar masses. Exactly, that's right. The mass of the Earth is about 10 to the 24 kilograms. Okay. And this is the Chandrasekhar mass we wanted to derive earlier. So what we've done so far in equating this maximum pressure from all these calculations in quantum mechanics we've done to get to the maximum pressure provided by these electrons in the star, and solving these equations numerically that describe the balance between pressure of gravity trying to collapse the star inwards and this degeneracy pressure trying to support against that collapse. We've come up with a maximum possible mass that these stars can support against collapse that is about 1.44 masses of the sun, and this is called the Chandrasekhar mass. And the accuracy of our result here is pretty good. This is, more or less exactly to 2 decimal places the accepted value for the Chandrasekhar mass. So we've done pretty well. And we've done it, right the way from thinking about the Schrodinger equation, thinking about how many electron states you can fit into a certain momentum interval. And we've figured all the way up from that how much mass you can have that will support against, how much mass you're allowed such that that pressure we've created from these electrons being crammed together can support against. And we've come up with a pretty good estimate for it, which is fantastic, I think. This is a really nice result. 4,747, some number Earths fit in that start in terms of mass. Oh, right, so you divided by the mass of the Earth. Yeah. Well, I mean, as a sort of order of magnitude for white dwarf stars, a white dwarf is something like a solar mass confined to the volume of the Earth. So, I mean, like you said, the mass of the Earth is about 10 to the 24 kilograms. The mass of the sun is about 10 to the 30 kilograms. So that means the density of a white dwarf is about 10 to the 6 times the density of the Earth. So a white dwarf star is 1,000,000 times denser than the average density of the Earth, which is enormously dense. So I mean, say you picked up an average sample of rock or something from the Earth that weighed 1 kilogram. Something like that maybe. You pick up something like that from the surface of the Earth, it weighs about 1 kilogram. If you picked up something that big in a white dwarf star, it would weigh about 1,000,000 kilograms. I mean, that's enormous. That's what, like 1,000 tons or something. That's ridiculous. Can you call it a dwarf? Well, in terms of size, you can call it a dwarf. So let's take a closer look at what we have here. So this, for those of you that weren't here earlier, this is a sort of rendering of a white dwarf star in a binary star system. So this is the Sirius system. You have, I can't remember if it's a red giant or not a red giant. Someone that knows more will correct me. But Sirius A is either a red giant or a main sequence star, and it's in a binary system with a white dwarf, Sirius B. And you can just kind of see very roughly here, the size comparison between them, how much smaller the white dwarf is compared to the sun. Because of course, a white dwarf is order of magnitude around the size of the Earth in terms of volume, but is around the mass of a sun. And as we've shown quite remarkably now, is around the mass of a sun, but never any more than 1.44 times the mass of a sun. This is an absolute limit on the size of a white dwarf, on the mass of a white dwarf, that we've calculated kind of fundamentally from quantum mechanics, statistical mechanics, some thermodynamics, and we've put it all together, and we've got a very nice sort of astrophysics result. Mosquitoes will be 5 kilograms. Do you mean like as in... I know what you mean. You don't mean they'll be 5 kilograms. You mean like something that would weigh 5 kilograms on Earth. If you put something of, or the mass needed on a white dwarf that would show on a scale 5 kilograms would be like a mosquito, would show 5 kilograms on a scale. Yeah, no, that's an interesting way of putting it. So yeah, if you put a mosquito on a scale above a white dwarf, the measurement would say 5 kilograms. But of course, what a scale measures is not actually mass. What a scale measures is weight. It just converts it, it divides by g. But I knew what you meant, so yeah, that's a great fact, awesome. How far are we from the density of a Schwarzschild radius of a black hole? Well, how big, what's the radius of the Earth? The radius of the Earth is what, like, I know it's got a 6 in it, 6,000 kilometers. So the radius of the Earth is about 10 to the 6 meters. Its mass is about 10 to the 24. So its density is about 10 to the 24 divided by 10 to the 18 or so. 10 to the 24 divided by 10 to the 18, that's about... Well, hang on, that can't be right. Wait, 10 to the 6... 10 to the 6 cubed, that's 10 to the 18. 10 to the 24 divided by 10 to the 18, that's about 10 to the 6. Wait, no, but there aren't 10 to the 6 kilograms. Hang on. What is the mass of the Earth? What's the mass of the Earth? Mass of the Earth, 10 to the 24. Am I being really slow? What is... 6,000 kilometers is about a million meters. Million meters cubed is 10 to the 18 meters. So the mass of the Earth, 10 to the 24, divided by roughly the volume of the Earth, 10 to the 18, that gives like 10 to the 6 kilograms per meter. But that seems ridiculous. There aren't a... Am I doing some really basic maths completely wrong? Ten to the 24 is the mass. Wait, someone help me out here. So the mass of the Earth is about 10 to the 24 kilograms. The radius of the Earth, yeah, I'm gonna blame it on the cold tea as well. Thank you for that nice comment. The radius of the Earth, let me look at that. Earth radius, what was it again? 6,000 kilometers. So about 10 to the 6 meters. So that means the density of the Earth, what, is like roughly 10 to the 24 over 10 to the 6 times 3, 10 to the 18, which gives about 10 to the 6 kilograms per meter cubed. Well, I mean, that's like a factor of 100 larger than it should be. But I guess... Oh, okay, according to Google, it's about 5,000. Yeah, so that is... Well, no, that's like a factor of 1,000 larger than it should be. Yeah, I know the 4 pi's and stuff. I guess maybe the prefactors are important. Well, anyway, let's leave it as an order of magnitude estimate. What was the question again? The question was about how far are you from the density of a Schwarzschild radius of a black hole? Well, so a black hole, Schwarzschild radius is 2gm over c squared. Oh wait, hang on. Are we comparing the white dwarf density, not the... Okay. So we got like the mass of the sun, in fact, squashed down into the volume of an Earth. So that's like 10 to the 30 over 10 to the 18. So that's, you know, order of magnitude 10 to the 12. 10 to the 12 kilograms per meter cubed for a white dwarf. For a black hole, you've got a mass m compressed to a radius rs. So, I mean, this is sort of average density. This is the average density within the Schwarzschild radius. Is, of course, is not the density of the singularity. That's a lot more totally different. The sort of average density of the Schwarzschild black hole will be the mass divided by rs cubed. So say you take a black hole that has the mass of the sun. So that's 10 to the minus 11 for big G, 10 to the 30 for the mass of a sun, over 10 to the 16 for the speed of light squared. So that gives you a Schwarzschild radius of about 10 to the 3. So about a kilometer. Oh, I see, you put a pi squared. Don't worry, they're all prefactors. I don't care about prefactors. We only care about order of magnitude estimates here at the moment. We've done our hardcore numerical stuff now for our 2 decimal place Chandrasekhar mass calculation. We only care now about this. So yeah, we get about 1,000 meters or about a kilometer. Yeah, exactly. As Matthew says in the chat, it's about 1.5 kilometers. So I calculate about a kilometer, the radius of a sun mass black hole. So in terms of density, that gives you about 10 to the 30 over 10 to the 9. So like 10 to the 21 kilograms per meter cubed. Oh, I feel like some of it's going to cut off. So that's 10 to the 21 compared to 10 to the 12. So it's about 1 billion times more dense on average. Or white dwarfs are about 1 billion times less dense than a black hole. So I mean, this is dense, but it's still not that dense, you know. And in fact, there's an intermediate between the two, between a black hole and a white dwarf. We can have neutron stars. And I can't remember off the top of my head a sort of order of magnitude density for a neutron star. These are things more like a neutron star is something like the mass of a sun confined to the mass of a city, like London or something. So what, say a radius of about, I don't know, on the order of tens of kilometers. Yeah, radius on the order of tens of kilometers. So, you know, something like 10 to the 30 over, say 10 kilometers cubed. Maybe it's just kilometers. I can't actually remember. But either way, that should be a 30. That gives us something like 10 to the 18, you know, for a neutron star. Now, this is a massive question mark because I don't know if I'm remembering roughly how big the radii are for neutron stars. But you can see there's an intermediate. So, you know, a neutron star is about, say, 1 million times more dense than a white dwarf. And the average density of a black hole, this is not the density of the singularity, this is like the matter that forms a black hole divided by the volume the event horizon takes up, or appears to take up, is then about 1,000 times denser than a neutron star, or about 1 billion times denser than a white dwarf. That's some back of the envelope calculations there. Then Strawberry Jesus said, how heavy would the piece of white dwarf rock be, counting the gravity influence on the surface of the white dwarf itself? Well, so for that, you could just take, you know, you could use Newton's law. You'd take the mass of the white dwarf times g over r squared, and that gives you like the gravitational field strength. So, you know, like the gravitational field on Earth is big G times the mass of the Earth over the radius of the Earth squared. Well, the gravitational field on a white dwarf would be the same, but it would be G times the mass of the white dwarf over the radius of the white dwarf, which in the example we were giving before, you know that the gravity at the surface of the Earth is about 9.81 newtons per kilogram. Well, on the surface of a white dwarf, you've got about 10 to the minus 11 from big G. The mass of a white dwarf, remember our rule of thumb was it's something like the mass of a sun put in the radius of the Earth. So that's about 10 to the 30 for the mass of the sun, and the radius of the Earth, what was it again? About 6,000 kilometers, so I'll just say 10 to the 6 meters. So that's divided by a 10 to the 12 there. So that gives you about 10 to the 7 newtons per kilogram. So this is about 10 newtons per kilogram, 10 to the 7. So, you know, everything you would weigh on a white dwarf star would be about 1,000,000 times heavier, roughly. Again, as a kind of back of the envelope calculation. So this is, you know, a lot heavier. You know, you wouldn't want to join a Weight Watchers club that happened to meet on a white dwarf star. Even less so on a neutron star. Even less so. Well, you can't stand on the event horizon of a black hole, but if you could, you wouldn't want to join their Weight Watchers. Size is measured by surface area. What do you mean by that? Oh, I missed all this size matters chat in the chat. Well, I think I'll leave it there. Okay. They would lose a lot of weight from the gravity. They'd lose a lot of height, certainly. I mean, they'd be, you know, pretty squashed down. And yeah, I guess, you know, doing cardio on a white dwarf star would be pretty intensive. Shame about, you know, no breathable atmosphere. Still very high temperatures. I mean, white dwarf stars are very slow cooling. You can use white dwarfs as like a bound on, I mean, not a good bound, but you can use them as a bound on the age of the universe, because white dwarfs cool very slowly, and the kind of the heat transfer within the layers is dominated by conduction of the electrons specifically. And the way they radiate heat is very, very slow. So they lose a lot of energy. Sorry, they don't lose a lot of energy very quickly. They're quite dim. Well, then actually, they're not that dim, but they've got a very small area, so the amount of energy that leaves is not very much. So they cool very slowly. Their temperature changes very slowly. And if you calculate the time it takes for a white dwarf to reach thermal equilibrium, you know, with the edge of the universe, not the edge of the universe, to reach thermal equilibrium with the rest of the universe, the time it would take is actually longer than the amount of time the universe has been around. So there are hypothetical. Oh, I think. Oh yeah, it's why MD just mentioned different types of dwarfs. So, oh, they mentioned white, red, brown, and sub-brown. I don't know what sub-brown is, but anyway, there's a hypothetical state after a white dwarf called a black dwarf, and this is just when a white dwarf, because again, it's not producing any more heat inside it, it's just slowly kind of cooling away. A black dwarf is what happens when it's, in theory, has radiated away all its heat and has reached thermal equilibrium with the rest of the universe, so it's no longer glowing. It's just a sort of black husk made out of neutrons, protons, and electrons. But the time it would take for it to cool down to that state is longer, or, you know, it's pretty close actually, but it's longer than any white dwarfs have been around, because it's around about the age of the universe so far. And of course, it took a little while for white dwarfs to actually form, because in order to get to white dwarfs, you have to have at least one generation of stars. You know, they're formed by the end states of these stars, so if you haven't had a generation of stars, you can't have any white dwarfs. Okay. What's in the chat? Oh, right. Oh, I see. Sub-brown is like Jupiter. Yeah, so brown dwarfs are totally opposite to white dwarfs. These are stars that never really are stars. They're stars that don't quite reach this critical mass needed to start undergoing fusion in their core, to start them burning. A brown dwarf is a star that's too small to initiate fusion, so never actually starts properly shining. I've never heard of a red dwarf. I didn't know that a sub-brown dwarf is like Jupiter. I guess Jupiter is, you know, composition-wise is gaseous and very similar to these brown dwarfs, but I suppose, I don't know, I mean, all these distinctions between how big something has to be a brown dwarf, how big does it have to be to a whatever. I don't know these distinctions. These are astrophysicist distinctions, and I think, like I mentioned before, I'm not an astrophysicist. I don't really know anything that I can't try and calculate myself, so I have no idea. Anyone entering the chat right now in the middle of the conversation will think we've just been talking about Lord of the Rings. Yeah, there is a lot of dwarf talk going on. Exactly. Strawberry Jesus mentioned, have you read anything on the ways of getting energy out of a black hole? No, not particularly. I mean, other than things like Hawking radiation, I've not generated devices located in the orbit of a black hole. No, I've not heard about that. I've not read about that at all. So Andy is not an astrophysicist either. Yeah. Well, that's good. Okay, well, I have been talking continuously for 3 hours, so I think I might pack it in there. But thank you very much for coming along. I'm pretty happy with the result we got, and the questions and chat afterwards was really great, so thanks a lot, everyone. Yeah, we got a pretty nice result, and I guess we'll leave it there. So thanks a lot for joining. Next Saturday, I'm not sure what we'll do. Maybe I'll put another poll on my Twitter, and we can someone can decide. Or if you haven't already, please do feel free to join my Discord, and then you can always recommend some things we could talk about in the future on there, or just we sort of chat about physics and share some notes and stuff occasionally anyway. So it might be pretty good. Oh, neutron stars. Yeah, that's a good suggestion. Maybe. I'll have a think. I'll see if there is anything else I'd rather talk about, but neutron stars would definitely be pretty fun. I've successfully distracted you from writing a paper on Compton. Thank you for the distraction. Oh, well, you're very welcome. Yeah, I would not want to write a historical paper on a physicist. I don't know. That doesn't sound good. But, we all have to do it as these assessments go. So, yeah, thanks a lot. Feel free to join the Discord. You love solving things with math and Matlab. Yeah, no, me too. Maybe I quite enjoyed the live coding aspect, actually. It was even quite enjoyable, the bits that went wrong, and we had to figure out what I'd typed in wrong. All these silly mistakes. So maybe I'll do that again more. Do some live coding to solve physics things. But like I've said, I'm not a coding physics person. I don't really use much numerical stuff, so it's all very basic, the stuff I can do programming-wise. I'm very much like a pen and paper, back of the envelope kind of physicist. But we can try and think of some other things. So yeah, join my Discord, and I'll talk to some of you on... So Tuesday, I'll do office hour, where, for those of you that don't know, you can just turn up and we'll chat about physics. You can ask me any questions you want to on Tuesday. And I think what I did last week that I probably will start off doing is when there are no questions coming in, rather than preparing something to talk about in advance, because it's meant to be quite casual, I'll just probably surf through physics memes on Reddit and maybe talk a little about the physics that they're describing, or maybe the physics errors that they're describing, who knows. But yeah, so join for that on Tuesday. Then on Thursday, I'll play some Mario Kart and we can chat more about physics then. Impromptus are the best. Yeah, I think so. Anti-gravity cat. What? Fair enough. Well, yeah. Anyway, I've got to finish somewhere. So yeah, let's leave it there. Oh, right, a meme. Oh, I see. Okay. Well, yeah. Thanks very much for joining, everyone. I'll see some of you on Tuesday, and yeah, come and join my Discord if you haven't already. Okay. Bye, everyone. Bye.